Hello, good evening. So, I welcome you in this NPTEL live session for the course Ultrafast Laser Spectroscopy. This is Shruti. I am the PMRF TA for the course. The course is taken by Professor Anindya Datta from Department of Chemistry, IT Bombay. So, would you like to introduce yourself, Nivid? You are the only person in the call, so I would like to know your background. Are you speaking? I can't hear you. Yes?
Yes. So my name is Dr. Nivi Chandra.
Yeah.
I teach here in a college in Bihar.
Okay. Okay. So, okay, you're a professor in there.
Yes, yes, yes.
Okay. Nice. So, what topics do you teach there?
I have to teach everything organic, physical, inorganic, everything. So
Okay. Okay.
huge
Yeah.
shortage of teaching staff here. So I'm
Yeah.
teaching
I see. I see. Okay.
at a BSc level, yes, of course, not to
Oh.
MS.
Huh. Okay. So that's challenging. Teaching everything.
Yes, it is. It is challenging.
Okay. So I'm a PhD student here. I'm in second year now, and I have to do this TSF. So let's start. Are you watching the lectures?
Yes, I am watching the lectures. I am right now in the second week. Yes.
Okay, okay. So is there any problem in that?
Not really, but I am liking course. It's at advanced level, so it is more challenging than other courses. And I'm quite fond of Professor Anindya Datta. I took his
Yeah.
quantum chemistry course also last semester, so I
Okay.
thought this time I will register for this course. Of course, this is little bit of at advanced level. It just so happened I have worked in fluorescence when I was in IT Guwahati, but sometimes you do things without understanding too much. Now I have a lot of time, so I think I should understand. Uh,
Yeah.
my
The
professors
course is
he
actually
also worked on time resolved spectroscopy. I have never used time resolved spectroscopy. I have only used steady state spectrophotometers. But
okay.
some people in my lab used to do time resolved measurements. Yes.
So for my PhD, I also don't use like this ultrafast spectroscopy. I basically do microscopy. So last semester only I had taken, like last year I had taken his course, and now I am the TA of the course. So
Mhm.
yeah, let's see how much justice I'll be able to do it. I'll try to explain or resolve your doubts as much as I can.
Okay, thank you.
Yeah. So for today, I'll just discuss the week 0 assignment because I'm not allowed to discuss the assignments before the deadline is passed.
Yeah,
So,
I understand that. Yes.
yeah. So week 0, there are basically only 5 questions, and I have added few questions by my own. So let's start discussing. So the first question asks, a laser light is characterized by monochromaticity, directionality, coherence, or greater speed than ordinary light. So this one is a very simple question. Now laser light, as we all know, is lasers are first of all monochromatic, which means it is a single wavelength. But there is always a width associated with any lasers, but for practical purposes, we say it is monochromatic. And ultrafast lasers also they have some FWHM associated with it. It is not purely a delta pulse, but for practical purposes, we can assume that it is a monochromatic. Next thing is directionality. So this is correct. Directionality. Now, directionality is the polarization associated with the laser. So all laser lights are polarized. So this is also correct. Next thing is coherence. Coherence means the all parallel nature of the laser. The all rays coming out of laser move parallelly. So this is the coherence. So the rays coming out of the beam is fully coherent, which means that they travel in one direction only. So this point is also correct. Next is the greater speed than ordinary light. So the light speed is constant whether it's laser light or any other light source. So this cannot be possible. So for this question, the correct answers will be first, second, and third.
Here, actually, I have some little bit of a problem understanding the directionality and coherence. You said the coherence is parallel, but that is the same thing with the directionality. It is also parallel.
No, directionality I think is the polarization,
Okay.
whether it's vertically polarized or horizontally polarized. And coherence is that all the beams travel together in a particular direction of the polarization. Okay, so yeah, so the next question is the unit of molar extension coefficient. Now, this term molar extension coefficient, this comes from Beer-Lambert's law, which says that absorption can be, not absorbance, can be written as epsilon times concentration and the path length. Now, this is what we call is the molar extension coefficient. So to get the units of this molar extension coefficient, we can just transpose this equation A divided by C times L. Now absorbance basically is log of I0 by I, where I0 is the incident light and I is the light which comes after passing through the sample. So the transmitted light. So since it's a log, it has no unit. So this, the numerator is unitless. We'll write it as 1. Then concentration is the molar concentration, molarity. And path length is generally taken here in case of absorbance in centimeter. So this is the uh, unit. Now molarity is mole per liter times centimeter. So when I invert this, it will be mole inverse liter centimeter inverse. So this matches with option number B. So here again the correct answer is B. Okay. Now the next question is about mode locked lasers. So do you know about mode locked lasers or mode locking?
No, no, no. I have no idea about lasers actually too.
Actually, this question is way too ahead of the course, where we will discuss mode locking and the ultrafast lasers later on. So as of now, simply tell the correct answers. Like mode locking is necessary to generate pulsed lasers. Mode locking basically is the constructive interferences of many beams inside the laser cavity. So it is useful to generate pulsed lasers, not the continuous wave, and it is not monochromatic, it is polychromatic because I told it has some width associated with it. I think in the week third or so, we will discuss mode locking. Okay. So now the next one is relationship between fluorescence quantum yield and lifetime. So this is the easier one. Now, lifetime, how is the quantum yield given? Fluorescence quantum yield is given by the radiative rate constant divided by the sum of radiative and non-radiative rate constant. So this is the fluorescence quantum yield. Hello Prakash,
Yeah, hello.
uh, can you introduce yourself?
Actually, I'm Dr. John Prakash. I work as a faculty in Central University of Tamil Nadu.
Sorry, I couldn't get you.
Okay, I'm Dr. John Prakash. I work at Central University of Tamil Nadu.
Okay. So, have you watched the lectures?
No, no, actually, I had to watch it. I just saw this mail, so I just want to see what is happening. That's why I just
Your voice is not coming properly.
I'm sorry. Actually, I just saw the mail, so I thought I'll just check it out. What is happening there. Sorry.
Okay, okay.
Yeah.
Okay, so here we are discussing the assignment questions. Like in the first week zero, we have 5 questions. Basically, we are discussing that only today, and later on we will discuss the assignments. That assignment dates are over, we will discuss those assignments.
Okay, actually, I think first one, zero one I did already. I think zero, right? It's discussing to zero, right? Assignment zero. Hello?
What? Yeah,
Are you discussing assignment zero or one?
I'm discussing assignment zero with some additional questions from my side.
Okay, that I know because I'm working on courses at Spectroscopy only. Okay, fine.
Okay,
Thank you.
okay,
Thank you. I'll join next class. Okay. Thank you.
yeah, sure. Okay, so this is the formula for fluorescence quantum yield, where Kr is the radiative rate constant and Knr is the non-radiative rate constant. Now, lifetime is also given as the fluorescence lifetime is given as 1 upon Kr plus Knr. Okay, so if I plug this here, it will be Kr times tau f. So this is the, okay, so in terms of tau f, we'll get divided by Kr. So this is the third option. Okay. So next is in in electronically excited state, organic acids become yes. So in electronically excited state, organic acids become more acidic, more basic, more oxidizing, or more reducing. Okay, so organic acids, suppose any acid, I'll take an example of the acid which is here phenol. Suppose phenol, which is benzene ring.
Actually, I have seen the lecture. It says it's more acidic, right? It
Yes,
will become more acidic. Yeah.
yes.
Since we are on the only one, so we can speed it up. Yes. It will save your time also. Yeah.
Yeah, okay, but anyway, I have to take the session for 2 hours.
Oh,
So suppose you know the answer, but there may be other students who will watch the recording and
acha,
will
acha,
not
acha,
be
acha.
able to
Okay,
hear.
okay, okay.
So
Okay, okay.
okay, so suppose we are taking the example of phenol. So we know it is slightly acidic, but when we see the molecular diagram, energy level diagram of this benzene ring, how the filling of electron is done. Let's say there will be 6 levels, and here we have when the when it loses the proton, it becomes O minus. So in total it will have 6 pi electrons and this one extra electron which will be delocalized. So let's fill the pi electrons 5 and 6. Oh, I did something. There is only one level. Okay, so and this is bonding and these are anti-bonding. So when the extra electron, and this is a ground state configuration. Okay, let's draw the excited state conformation as well. So in excited state, one of the electron will jump over here. So here we'll have only one. Okay. Now from this, the extra electron, when in the ground state, it when it is getting delocalized over this benzene ring, it has to go over here in the antibonding molecular orbital. Okay, but in the excited state here, this level is empty, so this electron can go over here, which gives it more stabilization because this is lower in energy. Okay, so that's why the acidic property is more in the excited state rather the ground state. So here the correct answer is first. Okay, Nivid, you may find the course little monotonous or way too easy for you, maybe because it is
No,
like,
not it.
yeah,
Yeah, fairly advanced course. Yes, yeah.
yes, because you already know the concepts, so it will be easy, but it's really difficult for students here. But the assignments are not so difficult because the assignments, majorly the questions are from the lectures itself, so it's
Yeah.
not that difficult. But understanding the course can be little. Okay, so the week 0 consists of these 5 questions only, and the coming questions are some additional questions which I have kept. So the next question is, the wave number of a transition ground state to excited state is 31250 centimeter inverse. And what region of electromagnetic spectra does this correspond to? Okay, so what is the relation between wave number and wavelength? Here I have added a diagram which shows the electromagnetic spectrum, and the energy scales are given in terms of wavelength. So red is 700 and the blue is 400 nanometer. So wave number, which we denote as u bar, is inverse of wavelength. So if it is 31250 centimeter inverse, we can we can find the corresponding wavelength, which will be 1 upon 31250 centimeter inverse. So if you will write it as 1 centimeter divided by 31250 and convert this centimeter to nanometer itself, so it will be 1 meter divided by 100 centimeters, and 1 meter will have 10 to the power 9 nanometer. Okay, so upon all the cancellations, we will be left with nanometer. So it will be 1 upon 123, 3125 into 10 to the power 6 nanometer. So this will come around. You can do the calculation, use calculator. This will come around 320 nanometer. And 320 nanometer is, this is UV region, ultraviolet, yes. Okay, so it is in the UV region. So it says UV and visible. It's not visible. Visible will start from 400 onwards. So we can consider this only because simply UV is not in the option. Okay, so next question is, as per the Lambert-Beard law, on which of the following factors does the absorbance not depend? Concentration, color, extinction coefficient, distance that light has traveled through the sample. Now, what is the Lambert-Beard law? As I wrote just now, it gives the relationship between the absorbance of a sample and its concentration. So it gives linear relationship between the absorbance and concentration of the sample at a fixed wavelength. And when we scan it through all the wavelengths, we generate the absorbance spectra. So it is given as log 10 I naught by I, which is epsilon times concentration times the path length. So I naught, suppose this is your sample cuvette. Okay, so the incident light is I naught, and when you will incident some light, some of it will be absorbed and the rest of it will be transmitted. A small amount will also get reflected and scattered, but we will not consider that. So this is the transmitted. And the path length L here is this path. The path which the light travels, the path of interaction of light and the sample. So this is the path length, and it is generally written in centimeter. So for normal cuvettes it is 1 centimeter. And C is the concentration of your sample here. So from the formula itself we can see that this depends upon the concentration, and if you increase the concentration you will not see the linearity. There is, so generally absorbance is taken in micromolar concentrations. If we'll take very highly concentrated solution, whatever the spectra you will generate, it may not be the correct spectra because there will be more scattering possible if because of the concentration difference. So suppose this is concentration versus absorbance, and there should be a linear relation, but for very high concentration, suppose this some threshold CT, there we will see that this either goes up or this either goes down. Means there is a deviation from linearity. If it goes like this, we call it negative deviation. If it goes like this, we call it positive deviation. So it is suggested that we always take the absorbance in micromolar concentration. And in this micromolar concentration, the absorbance will come from 0 to 1 in between. Okay, so to answer this question, it depends on the concentration, which is correct. It depends on the extension coefficient. Yes, now the extension coefficient, so extension coefficient is the ability of the sample to absorb light. Suppose a sample which has, that there may be two samples having same path length and concentration, but if one sample which has more absorption cross section or the extension coefficient, it will absorb more light and its absorbance will be high. So it indirectly tells you the capacity of a sample to absorb light. So it depends on the extension coefficient as well, and distance that light has traveled through the sample. Of course, this distance, if you pass more light, pass light for more distance, this will change here. The L will change, and accordingly the absorbance will change. Okay, and it does not depend on the color. Okay, so whatever the observance will be fixed, suppose, because it is per wavelength. Suppose this is suppose my observance spectra of some sample at this wavelength. Color means the wavelength lambda 1, at this wavelength lambda 2, and at this wavelength lambda 3. If we change the anything concentration or path length in this, still we will get this same kind of line shape for this sample. So it is wavelength independent. So here it does not depend upon, okay, so the question asked it does not depend. So it does not depend on the color. Okay, let's move to the next one. Now shift of spectrum maxima peak position to a higher wave number corresponds to shift to lower wavelength, shift to higher wavelength, loss of intensity, shift to lower frequency. Now shift, this is again related to the relationship between the wave number, wavelength and frequency. Now let's start from the formula. Energy E, which is h nu, is given by, in terms of wavelength, it can be written as hc by lambda, or since wave number is 1 upon lambda, it can be written as hc nu bar, which is wavelength. So shift of a spectrum maxima to higher wave number. Suppose we have a, this is nu bar and here is the intensity. So this is nu bar 1, and after some process or something happens to the sample and it changes its spectral peak position to here, which is nu bar 2. This is nu bar 1. So here nu, it is higher. Okay. So in terms of wavelength or frequency, what will it be? So we can see there is a direct relation between frequency and wave number. So if wave number is increasing, the frequency will increase. So in terms of frequency as well, it will be the same shift to the right side. But there is an inverse relationship between wave number and wavelength. So if we'll draw it in terms of wavelength, we will have, initially it was like this, lambda 1, and later after the change it will be like this here, lambda 2. So here lambda 1 is greater than lambda 2. So it, in terms of wavelength, there is a shift to the lower side, this side. So shift to lower wavelength will be the correct answer. There will not be any loss of intensity because it does not depend on which scale you plot the graph. The intensity will not change, the spectral intensity will not change. Shift to lower frequency, no, it should have been higher frequency only. Okay, so here the correct answer is first. Okay. The next question is about polarization. So magic angle for polarization. Nivit, do you have any idea about this?
Yeah, it should be 54.7 degrees Celsius, I think.
Yeah.
This is also used in NMR, yeah.
Yes. So wherever we have this anisotropy factor, we need to minimize the anisotropy. We use this magic angle. We excite the sample at magic angle, whether NMR or steady state fluorimeter or in TCS-PC or in optical grating, anywhere where we need to minimize the effects of anisotropy. So this magic angle comes from one mathematical, so equation is 3 cos squared theta minus 1 should be 0. Okay, now this is needed and you will know about it in anisotropy lectures. So it is discussed later in the course. So I'll simply take over from here that when this 3 cos squared theta minus 1 term goes to 0, we say there is no anisotropy in the system, and for that the we need to calculate this angle theta. So this will be 3 cos squared theta equals to 1, so which will give cos theta is equals to 1 over 3 under root, and when you will solve this, theta will be cos inverse 1 upon root 3, which comes out to be 54.75 degree, approximately you can say 55 degree. So this is the magic angle for polarization, 54.7 degree. So there is a, suppose in TCS PC or in TCS PC, first we use, so to excite the sample in order to collect the fluorescence decay, we can, there are ways to excite the sample. So we can excite it by the fundamental wavelength of the laser, fundamental, or we can use the second harmonic, or we can use the third harmonic. Okay, so if the fundamental wavelength is,
Actually, I have a doubt here.
yeah,
Uh, my doubt is that in these harmonics there is not 100% conversion, right? So intensity of the laser will be reduced.
yes,
So one very big advantage of laser will be lost if we go for at least third harmonic.
yes,
Intensity will
yes.
be reduced. Why don't we just change the laser and appropriate laser?
Okay, but because, so for third harmonic we used to generate high energies in the ultraviolet regime, but
Hmm.
but the appropriate material to emit those wavelengths are not available generally. So we use the, like, lower wavelengths, lower energy to make second harmonic, third harmonic, and so on to generate those higher energies.
It is because of the non-availability of appropriate lasers.
Yes, appropriate lasers. Yeah.
because one big advantage is lost because laser is very intense, but with these harmonics, I think intensity will be much
Yes.
reduced.
So for biological samples and all, they excite the sample using the third harmonic. First of all, it will have less intensity and it will not damage the sample much, the biological samples, and also there is they get excited in like deep UV. So deep UV can be generated using, suppose you are taking 800 nanometer, so you can generate second harmonic as 400 and third harmonic will be 800 by 3 something. So like this you can generate the higher energies. Okay, so what I was saying here is fundamental. Suppose if this is vertically polarized, the second harmonic will be horizontally polarized, and the third harmonic will again be vertically polarized. So if we want to excite the sample using the third harmonic, you need to keep it in the like this angle is with respect to the fundamental, so 54.7 degrees, so which is true for second harmonic. But in case you need to do for third harmonic, you need to subtract it from 90, 54.7, so it will come somewhere around 35 degrees. So when here you have to change the polarization angle in the instrument in the TCS-PC to 35 degree. Okay. Okay. So the next question is, if a fluorophore has absorbance maxima at 385 nanometer, its emission maxima is likely to be smaller than 385, greater than 385, equal to 385, or not enough information to say. Now, there is some rule which dictates uh, this kind of behavior of fluorescence. This is called the Kasha's rule. Now, Kasha's rule says that the emission occurs from, wait, I'll write here, emission occurs from the lowest excited state, which may be the S1 state or T1 state. Okay, so I have a diagram here. So suppose this is our ground state S0 and this is some singlet state, some singlet S1 excited state. And if you have excited the sample with up to this vibrational level, so the emission will not come exactly from here. It will undergo relaxations up to the lowest vibrational level of the excited state, and then it will give emission. Why is it so? Because this relaxation process is much faster. So the rate constants are much faster, higher, and hence this process occurs very faster than the emission comes out. So emission generally comes out from this lowest V0 level of the first excited state. So this energy gap is smaller than whatever was our excitation. Okay, so smaller energy gap means it will come at higher wavelength, right? So this thing is called the Stokes shift. So if you have excited your sample here, and if the sample is very ideal and have the exact emission, so it should have been come over here, but there will be some shift because of this uh, relaxation process, and the emission is coming out from the V0 level. So this shift is called the Stokes shift. And the Stokes shift, it is coming at higher wavelength. So suppose here we have 600, suppose 625 nanometer is the emission, and you might have excited here at 535. So this difference is your Stokes shift. So here in this question, it asks that if a fluorophore has absorbance maxima at 385, its emission maxima will be smaller, greater, equal. So it cannot be smaller than 385. At max, it will match exactly, and the emission, so suppose in some rare case it may happen that it is coming exactly from here. This will be the ideal case, but it can never be lesser, it cannot come from here. So larger energy means smaller wavelength, so it cannot come from smaller wavelength. The emission will not never come from smaller than 385 nanometer, it will always be greater. So when we take this emission spectra, when we take this steady state emission using some spectrophotometer, so if you have excitation wavelength you have set, if your excitation wavelength you have set suppose 405 nanometer, then you have to collect the emission at least 10 nanometers ahead of the excitation. So we can calculate the emission from 450 nanometer. So this 10 nanometers can be our Stokes shift. It may possible that you may have to collect it more than 415 nanometers, but to start with we can give that initial wavelength as 415 to 650 or 700, depending upon your sample emits in visible or IR or anything. Now the next question is about refractive index. If the refractive index of a medium is higher than that of air, speed of light through that medium will be higher, lower, or unchanged. Now, what is refractive index? Now, refractive index is defined as the velocity of light in vacuum suppose I write it as c, which is a constant, divided by the velocity of light in the medium whose refractive index you are trying to calculate. In the medium, let's write it as v given by eta. Now since this is equals to c by v and this is a constant, so if n increases, so if eta increases, this has to decrease to balance to get this constant. So if the refractive index is higher than that of air, now what is the refractive index of air? It is 1, approximately 1, slightly more than vacuum, but we can say 1. So if it is more than 1, suppose for example in water, ice, glass, diamond, in these things the refractive index is more than 1, which means that the velocity of light in these medium are smaller or lesser than the velocity of light in air. So here the answer will be the speed of light through that medium will be lower. Okay, coming to the next question. Now, emission without change in spin multiplicity. Phosphorescence, spin forbidden, fluorescence involves intersystem crossing. Here is a diagram which is called the Jablonski diagram. Now, it says that these levels are the electronic energy levels. So, one electronic energy level has in it many vibrational levels, and inside the vibrational levels there will be many rotational levels. So here rotational levels have not been shown, only the vibrational levels have been shown. So first is, if you will excite this, so at room temperature most of everything will be in the ground state. So when you will excite the sample or give it enough energy, it absorbs light energy in form of light, and it goes from ground state to excited state, which can be S2, S1 depending upon the energy it absorbs. Now these are singlet states. So there can be intersystem crossing where the molecule or the sample goes from the singlet state to triplet state, and then it can lose its energy by vibrational relaxation and give some light radiative transition, or it can go non-radiative transition. If this transition is radiative, it is called phosphorescence, and it is from T1 to S0. Now, phosphorescence T1 to S0, and since the spin multiplicities are different, it is spin forbidden. Here the spins are changing, but if the sample doesn't undergo this intersystem crossing and it doesn't go to the triplet state, it will relax to the zeroth vibrational level of the S1 state, and it may undergo radiative or non-radiative transition from that state. So if it is radiative transition, we call it fluorescence. Now fluorescence FL is from S1 state to S0 state. So here it is spin has not changed. So spin is conserved, and that is what the question is asking, that emission without change in spin multiplicity is called fluorescence. And it does not involve intersystem crossing. Intersystem crossing is needed for phosphorescence, which is in which the spin changes. Okay. So these questions are numerical questions, and I give this I leave this question up to the students to practice. So I'll simply discuss it, but will not tell the solution here. So this question is asking about fluorescence, the advantage of measuring fluorescence over the UV visible or the absorbance spectroscopy. So why the fluorescence is more, measuring the PL is more advantageous than measuring the absorbance? Nivit, can you comment over this?
It is sensitivity.
Yes,
Sensitive.
but why is it sensitive?
I have no idea.
Okay, so it is because in absorbance or in UV visible spectroscopy, what we do is we take a reference and then we take, so it is I0 by I. Okay, so first we measure the initial intensity of the light and then the intensity which gets transmitted. So we are measuring two intensity levels. But what happens in case of fluorimetry? There is no light initially. So when the sample emits light, even a single photon gets detected because there was no light in the background before the emission. So it's like seeing something, seeing a small light in a dark room. Okay. So if there are so many lights around you, you may not see a small bulb glowing. But if the room is completely dark, a small LED you can see. So it's like there is a background associated in the absorbance spectroscopy, but in fluorescence it is, the background is dark. So a single photon gets detected. So that's why it is more sensitive. Okay. So the next question is true statement about fluorescence spectroscopy. Emission usually occurs at energy greater than the energy of excitation, which is true, which is called, sorry, it is not true, it is opposite. It is written in terms of energy. In terms of wavelength, it occurs at higher wavelength. In terms of energy, it occurs at lower energies. Okay. So next question is, metabolite M was isolated from cerebrospinal fluid after excitation at 280 nanometer. The material fluoresced at 360. The Stokes shift for the assay will be. So the excitation was 280 nanometer and the fluorescence, the emission was 360 nanometer. So how will you calculate the Stokes shift?
Just subtract both of them, so it will be
Yes,
80.
so it will be initial wavelength minus the excitation wavelength. It will give you the Stokes shift. So I think it will come around 80 nanometer here. Okay, next is extension coefficient of NADH 340 nanometer is 6440 liter per mole per centimeter, whereas NAD does not absorb at 340 nanometer. So there are two species, NADH, whose absorbance at 340, whose coefficient at 340 is given, and there is another species NAD which does not absorb at all at 340. So the extinction coefficient is almost zero there. What absorbance will be observed when the light at 340 nanometer is passed through a 1 centimeter cuvette containing 10 microliter NADH and 10 microliter NAD. So it's a mixture containing these two solvents. So now absorbance is a additive property. So if there are 2-3 samples, the absorbance gets added. So we'll have absorbance of NADH plus absorbance of NAD at 340 nanometer. But the question says that NAD does not absorb at 340. So this is 0. So it will simply have the absorbance of NADH, for which we have given the epsilon NADH into the concentration of NADH, which is 10 microliter, and the path length of the cuvette is 1 centimeter into 1 centimeter. So it will have this into 10 micromolar. So this will be the absorbance, whatever comes out after the calculation. So the next question is the absorbance of copper sulfate solution containing 0.5 mg copper per ml was reported as 0.35 at 440 nanometer. Okay, so there is a copper sulfate solution whose concentration is given, whose absorbance is given at a particular wavelength. Calculate the specific absorptivity including units on the assumption that 1 centimeter cuvette was used. So now specific absorptivity is same as the molar extension coefficient. It is just the different name. Just epsilon. So here we have been given A. A is equals to epsilon CL. So A is given 0.35. Epsilon we need to calculate, and concentration is given 0.5 mg per ml, and path length is 1 centimeter. So we need to take care of the units, and we can get the epsilon from here. Now for a sample, epsilon is constant. It does not change unless you change the sample. So it is the specific property of the material, inherent property of the material, you can say. The sample or the material, or so whatever you are measuring, the specific absorptivity is it will not change even if you change the concentration, or it will even if you change the path length or anything. So the next question is, what will be the absorbance if the solution is diluted to twice its original volume? So the concentration has been decreased by 2 times. Path length remains same. So what will be the absorbance? So for here we need the specific absorptivity, which we have calculated in the first part. We can use the same value and calculate the absorbance. So I think everyone will be able to do this. Okay, so here the last question here is fluorescence quantum yield and fluorescence lifetime of a molecule are 0.4 and 5 into 10 to the power minus 9 seconds respectively. So this is 0.4 and lifetime is 5 nanoseconds. If the fluorescence decay rate constant is y into 10 to the power 7, the value of y. Now, fluorescence decay rate constant, what does this mean? This means the Kr. So, Kr is given by this into 10 to the power 7 second inverse. We need to calculate the value of y. Now, we know this fluorescence yield is given by Kr divided by Kr plus Knr, as I told in the first question, in the initial questions. Now, this part is the quantum, is the lifetime, Kr plus Knr. Okay, so I can plug that Kr into 1 upon Kr plus Knr. This will give as Kr into tau f. So this simplifies it. So we have to calculate Kr, this property. So Kr is equals to tau, quantum yield divided by the lifetime. Now quantum yield is 0.4, lifetime is 5 into 10 to the power minus 9. So, and the rate constant, this is second. So rate constant will come in second inverse, and you have to put the order here as 10 to the power 7, adjust the uh, like orders of this power of 10, and this will be second inverse. So whatever factor comes here will be the answer, rounded off to the nearest integer. Okay, so that's all. I got these many questions for today. If you have any doubt, you can ask. I'll try to answer.
One thing I want to know, this pulse laser, this pulses thing. I mean, is not the laser being shined continuously?
No,
Huh.
it comes as pulses, but
Hmm.
but when you will see a pulse laser, you will feel or think of it as a continuous only, because the pulses come so fast that our eyes cannot detect it.
So that many times the laser is switched on and off, is it? Or we do it in some
No,
different
laser
way?
is switched on only once, but because of this property called mode locking,
Hmm.
the laser is on throughout, but the pulses
Okay.
comes only after a certain time period.
That is because of interference thing, right?
Yes,
Okay.
whenever that constructive interference happens, the pulse gets like the intensity gets too high, and that comes as a pulse.
Okay. So basically, the laser is on all the time, but we see the pulses because of this mode locking.
Yes, yes,
And the other thing is, by visual inspection, we will not be able to tell whether it
yes,
is
yes,
continuous or pulsed. Okay.
yes. Okay, so is that okay?
Yeah, it's okay. Thank you.
So I'll close the session now then.
Yes, you can. Please. Okay, go ahead. Okay.
Yeah. Thank you. Thank you for joining.
Thank you.